Okay, okay. So slides are visible, I believe, huh?
Yes, 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 sir. Yes, sir.
Okay, fine. So let us start. So discuss today MIMO antenna for wireless communication. Particularly, we'll see here different associated MIMO antennas, and we'll also talk about the history actually, from where actually this subject started, and what is the state of art. We'll see, and followed by the printed MIMO antennas, what we developed here, followed by some of the isolation techniques, what we verified in a lab, correct? So, as I already mentioned about my research group earlier talk, okay, so 6 PhD already graduated from the lab, and 5 full-time PhDs are working with me along with some PhD student as a part-time, as well as I as I'm co-guide of some of the student also, and particularly the research interest now the mathematical metabolism and cognitive radio antennas, and we are also working in mechanical absorbers, okay, and of course we are actually in DRA, so we are working towards this, developing the circularly polarized DRA. Apart from that, structures like you mainly heard about these things: electromagnetic band gap structure, artificial magnetic conductor, FSS. These fall under the FSS category. The lab is sponsored by mainly DRDO, CRB, DST, TQ, and institution as well. So the outlines here. So we'll start and we'll try to understand the design procedure for multifunctional antenna, which is the current requirement nowadays. We'll also see the history of the MIMO, okay, followed by the parameter, what parameters we need to study, and we'll find the importance of the current scenario, okay, and try to see its application in LTE, and we'll also see that how this MIMO is helpful for 5G at sub 6 gigahertz and the millimeter wave as well. We'll also see the types of printed MIMO antennas and also what isolation techniques are available in the literature. I'll show you different techniques at how you can the isolation. Finally, I'll show you the research work what we done at IIT Ahmedabad, and this is focused on the multifunctional antenna, MIMO antenna, and antenna with the MIMO antenna with high with good radiation characteristics. But how we can get actually the good radiation characteristic by using the AMC or other FSS will also show these things. Motivation. So it's very important nowadays, correct, and is an integral part of our life. So like when you aware or maybe not aware that phone actually launched by the Motorola, and this person Martin Cooper, called us father of cellular phone. Okay, so he's an American engineer who led the team in 1973 to build the phone. Correct. So we started the commercialization start from 3 for the domestic application, and from there actually we have seen number of devices like Nokia, BlackBerry, LG, Samsung. Now we are actually correct smart mobile phone. We can perform the number of operations with in our daily life. Okay. Very correct. If you see mobile, correct. So there are n number of technologies are available. Okay, among all the technologies, there is a one thing, antenna and this RF circuit is very important. Correct. talk about the antenna, so suddenly the next thing is coming in our mind, that speed, internet speed, connectivity, and all those things. Okay, so mainly for the antenna engineer, or for us actually, this is a very interesting thing, that how we can make it efficient. Okay, so that we can perform all daily routine work on our mobile. Okay, so now here, like people talking about the internet of things, correct? So like when internet of things, so the actually coming in our mind, which are the smart cities, smart vehicles, okay, healthcare system, okay, education. Now we can see, okay, without internet it is not possible, this virtual uh, things, lectures, or this discussion. So this is really very important. For this actually, good internet connectivity is required. Fine. So nowadays, like, about the 5G, okay, sub 6 gigahertz and the millimeter wave as well. And soon, like, um, new mobile phones are coming. Like, let's take an example of uh, Apple iPhone, okay, 12. Okay, so if you check the specification, you will find there are bands actually for sub 6 gigahertz. Even in Apple 12, actually, they have given the provision for millimeter band also. As far as I remember, I think this is given actually. So keeping the things for the future, they are introduced these things. So definitely in months we may be using the subsystem 5G communication as well. Correct. So we may have the internets and the connectivity. Fine. So for that actually, this MIMO played a very important role. If you remember the 3 or 2G time, there is a frequent loss, okay, connectivity, several issues are there, correct? When this or LTE came in 2010, and then LTE, okay, or the 4G actually, what we are commonly knowing this term as the 4G, is 2016 or 17. Suddenly the things were improved, particularly the connection losses and other things are now very stable actually. We are not losing a call very frequently, and the connectivity very frequently. So there is a very major part, okay, of this MIMO technology. Okay. So like and MIMO technology, like it is that MIMO antennas, because diversity actually, the term diversity derived this all the things. I'll explain the historical part of MIMO. Fine. So like here you can see the design procedure of the multifunctional antenna, see circuit module. So here you can see that if we want a multifunctional antenna, so what is the things are required? So one is a antenna required. Another thing is we have to define a multifunctional circuit which can act as a all band pass band. So when we are combining these two and doing the and then further the routine process, so we may have multifunctional antennas. Correct. So what is multifunctional antennas? We all aware that this we want to handle the number of operation in a single device. Okay. So for that we require device which could handle, which could manage all those things. If the device have capability, okay, to switch the frequency from one frequency to another frequency, it is really a great thing for us. In this way, we can miniaturize the device as well, okay, and it would be less complex, okay. Now the thing is, people are talking about the 5G, so this subject is coming very frequently when the antennas. We are talking about the antennas. So mainly, like if you compare the 4G and 5G, so 5G actually better than this 4G. Okay, this is the magazine actually you can. this magazine. So is your city ready to go digital? Okay. This article is very interesting actually, and I have taken a picture from there. Okay, so here they actually define 8 ways, parameters over there. 5G technology better than the present technology. So one is the latency. It's very important. Okay, so latency is than 1 millisecond. Okay, it's very fast. Okay, then we have the device density more than 1 lakh. Sorry, 10 lakh per kilometer. When we have the more device density and all handled by the 5G system, data rate is extremely high. Like the advanced 4G system, what we can go up to a 1 gigabits per second. Whereas for 5G, actually, we can similarly the other things like power consumption, bandwidth, spectral efficiency, and reliability. Everywhere, actually, these things are is uh, better actually as compared to the present one. Okay, so this is the different band accepted in different countries. Okay, and mainly this 3.2 to 4.2. So when you are designing your antennas, MIMO antenna, you can keep this number and you can design in this band. Okay. So let us cover circuit. It's very important. We should know about this thing. That like this is particularly for gigahertz 9K. This is for GSM band. Okay, so we have the analog signal circuit and we have the mixed signal circuit, and then we have the digital the operation will be performed. Now this is our area actually where the analog signal circuits are there, antennas are there, then we have the power amplifiers are there, low pass filter, these things are there. Correct. So now like here you can see the thing distributed. Okay. Now here if we combine within a single chip, it would be a really a good thing for us. Now if you talk about the implementation part, okay, so definitely we should do the circuit first. Okay, we should learn about biasing circuit, different active and passive devices, followed by how we will manage it on the substrate. So print circuit board, which is a very common among the RF engineers. Okay, so this is the realization. Most of the these things participants may be knowing about these things. Okay, so realization of this RF devices. So we have to use surface mount technology, microstrip realization. Okay, and some chip registers, inductors. Okay, and maybe sometimes capacitors also. Okay, we need to manage it. Fine. So like this mobile, so we have a number of things. Okay, we have a number of things. Apart from that, we are actually very focused towards the antennas. Correct. And here, if you see, so we have the two antennas here: LTE antenna, horizontal polarized, and LTE antenna, vertical polarized. Correct. So we have like in my last talk, I already discussed this. We have the circularly polarized LTE antenna. It would be very great thing. So you can develop okay, which having this kind of capabilities. Okay, so this is one of the old mobile Samsung Galaxy S, where the number of antenna distributed over the correct. So this is actually the 3G one. Okay. Now, as I told, we should focus about. So here we can see the antennas are there, and these are the MIMO antennas. Correct. MIMO antenna when the LTE started, this 2011 and 12. Okay. So this MIMO antenna in this MIMO technology actually, we improve the reliability as well as data. Okay. So now we have a number of things, correct, as we discussed in our last lecture as well. Make the common antennas. We have circular polarization. So we in last talk, I already told about how we can get the circular polarization, different technique, different things I have already shown. And this particular thing is very important, that how we would introduce isolation so that it is not going to affect other things, others. multifunctional. Okay, it's very important. And finally, the modern MIMO cognitive video compatibility. So this fifth number, okay, we would be stressing over here how to develop these MIMO antennas, which could be compatible actually with the present technology. Correct. So when we say the MIMO actually is like here we have a transmitter and we have a device, our mobile. Correct. So here you can see this is a 4x4 MIMO device. Correct. 4 transmitter and 4 receiver. Now this picture is really very good actually, and we may guess a number of things. Like here you can see the two antennas are there, okay, and the users are distributed in a building, over the ground, in a car, correct, in a different places. And here you can see the red, which are the signal is going to block by these obstacles, like obstacle maybe building, maybe trees, maybe cars, okay. And apart from that we have the reflected signal to the green one, correct. So like uh, if I'm recalling the 2G and 3D, that is a the line of sights are very important, correct. There is a the signal, correct. But if we provide somehow the diversity, maybe frequency in a space time, correct, or antenna diversity, we may actually we may handle this loss of signals, correct. So this present scenario, the N communication is nowadays is there actually all of the devices for non-line of sight communications, correct. So that is why here the idea of the MIMO is very, because if we provide the okay. So there is actually that receiver may receive from any of our antenna. The signal may be received by any of the antenna. Okay, and in this way we may save our losing the signal. Correct. Now let us try to understand first the history of MIMO. We'll start back 1920s. New subject. We start with 1920s. And particularly this, when we are talking about the modern MIMO technology, this term derived from the antenna diversity. Okay, so first antenna diversity, this terms came. Then after this MIMO technology and other things are propagated. Okay, so this is actually is the experiment of RC engineer. RC this things engineer. Harold and the beverage. They started this thing. Then what is the observation that time, that radio broadcast at two different stations had different signal strength. They observed fading due to the multipath propagation. Okay, as we discussed in the last slide. And what they contributed, a diversity system which combined audio output of two receivers to get improved quality signal. Okay, so finally what they concluded, that the antenna should be separated by at least wavelength for reliable operation. Okay, so this was the observation in 1920s, by these two engineers actually. Now, so then after a lot of things happened actually, and particularly I think some of the important where the development from 1941 single radio receiver which switches between the two antennas, okay, 300,000, and what they presented the average signal to receiver to provide the immunity to fading. Then after 1959, a sophisticated radio with understand signal processing, okay, improved method of diversity, and few algorithm was proposed. Okay, 96. Okay, so they assuming antenna unaware of multi-channel transfer function. H transmitter communication capacity they have given with this formula is very well known. So he proposed opportunity for large data using the multiple radio and also provided basic communication architecture realize the available capacity. Then after Relay and Coffee in 1998, they provided the space-time coding, okay, structure to capture some of its available capacity in multipath, and did the strong connection between capacity and single value of channel. They postulated that even a large channel capacity is possible if transmitter is unable. Almost in 1998, he presented transmit diversity scheme that provide the optimum pre-link and exploit multipath channel when the transmitter is unaware of the channel. So pre-MIMO era basically focus delay and correlation between of signal of two antennas. Okay. Now let us have this graph is very interesting. So like many studies you will find actually use the antenna system particularly, okay, and also develop antenna information regarding this multipath propagation. So like here if you see this curve, so y-axis is the megahertz, okay, this is Mbps, and this is x-axis is year. So pointed here 2 points with 1997 and 2009. Now, like here, if you see in 1997, we have the speed of 2 Mbps. As soon as we got this MIMO capability, okay, to WLAN, we have actually 300 Mbps. Okay, so this drastic change. Okay, so this is actually the evolution of the local wireless network dates over the time. Correct. So this is possible with 4-stream MIMO. Correct. So what of the modern wireless system? Correct. If we see, so we require the improved reliability, and we require a channel capacity, and the solution MIMO antenna system. Correct. But there is a catch here. What is the catch? The catch is antenna elements are very closer, so there is a high mutual coupling. There is a crosstalk, which reduced particularly the mean performance. That the communication is not as efficient, but theoretically what we are expecting. Okay, so the big challenge here, engineer, is that how to reduce now this mutual coupling. Correct. So you will papers. Okay, you will see the number of papers. Okay, and where these things are explained that reduce this. Okay, now let us try to understand, okay, the evolution of the MIMO, and particularly from 3G. Actually will not go before that, okay, because we know this thing. So when we started this 2004 this 3G system, it was single input single output. Okay, maximum 384 kbps speed. Okay, we remember these things, okay, because that time we use the mobile. We struggle a lot, okay, to get this information. Then after LTE introduced 2009 and it was actually single user MIMO, okay, and it comes with a 300 Mbps speed. Finally 2016 and in our hand we cell phone which having the multi-user MIMO, and the speed was, and now we are expecting the massive MIMO which can give you the 20 GB speed. So particularly we can see the things in a two windows. Okay, window is that below 6 GHz and above that we have a section which is between 3 gigahertz and 100 gigahertz. In between, focus is on how to increase the capacity. But when we are talking about the below 6 gigahertz, so the main thing is that the coverage as well as the capacity, both the things. Okay. So these are the communication systems, actually different communication system. We are aware actually like CISO, single input, single output. We can hear the transmitter side one antenna and the receiver side only one antenna. They are receiving the signal, right? Then after we have CINO, which is a single input, multiple output. Okay, so at the output side we have diversity. Okay, now if you see MISO, so we have the transmit diversity. Side we can have the provision sending this signal from the two different antennas. Correct. Now finally we have MIMO. Okay. We have at the diversity at the transmitter side as well as the receiver side. So the next question actually, that why this? Okay. So I already told about this thing. So and we'll try to understand parameter and different things, but how it helps actually to improve the diversity as well as the channel capacity and other things, that how it will improve the bit rate. Okay, we'll see all those things. So particularly the answer is that we have of the data rate enhancement. Okay, so that is of business we are doing here. Okay, but within this actually we have like if we talk about the early communication. Okay, like we are in 2002 or 4 when the speed was in kbps. Correct. From that time onwards, the requirement of the data speed was needed actually, and that is why subject actually come into the picture. And that time the limitation was like available spectrum. Okay, so we know spectrum actually that particularly Shannon channel capacity of single input, single output. For that, if you are to increase channel capacity, so we increase the bandwidth. Okay. Second thing is have the infinity spectrum. So because the ITU is allocated and they specified, so we don't have this infinity spectrum. So that is why we need to find some alternative ways so that we may fulfill actually our requirement within the allotted bands or channel. Correct. Second was actually that energy efficiency. So the transmitted power level is we because they want the greener and safer communication, and through this high power increase but this create a biohazard. Okay, so still this is challenging. We cannot have very high power. So certain limitations are there. Okay, within that we have to work. So with this, when this MIMO antenna MIMO antenna came. So finally, it was hope that yes, we may increase actually, or we may find the solution to overcome these problems. Okay, so particularly what are the try to understand. The challenges are the mutual coupling, first thing, as I told you. Then there is a correlation between in a far field region. There will be correlation. Like we are measuring the ECC. Okay, so we need to improve these things, correlation coefficient. Another thing in the number of ports. Okay, so it improves the system capacity. Okay, actually offering the number of crosstalks. Okay, and the thing is, second is reduce the overall footprint. How to reduce the overall device, electrical size of the device. Okay, so as I already given the much idea about that how we can reduce the electrical size of the antennas and stuff. Correct. Let us understand one by one with the advantages and disadvantages. Important. First is single input, single output system. So here you can see we have a transmitter and receiver. Okay, and the best thing is that we have the design, and this is a low cost 2G and 3G system. Now the disadvantages, the things are there, like it offers the multipath propagation, correct, and signal strength degradation due to the multiple reflections and all, and fading, interference and multipath fading. And the channel capacity is already 1948, used number of times this formula, correct, and it is limited by the Shannon law, okay, which is written, and theoretically maximum at which the free digit propagated in presence of the noise, correct. So with the, we have a number of limitations. Now, sorry. Now, due to the degradation of the signal strength, okay, so we have the two major, okay, we already experienced these things. One is a reduced link capacity, and another is low link reliability. Okay, means losing the signals all the time in our mobile. If you remember this thing, and link capacity is as well, not continuous. Now, this is somewhat very interesting actually, and we should understand those who are is diversity. So diversity, what is diversity? So this is to overcome the disadvantage of SISU system. Okay, so this diversity actually was so like the thing is we have the different type of diversity schemes, correct, like space, time, and frequency. Similarly, that fades independently. So this is a good thing. Introduce a number of diversity schemes, so we may have the high reliability. These things, okay. So it will increase in means receiving data probability will increase, reliability will improve, and the signal degradation decreases, and the link performance will increase. Okay, so like if you are talking about the space, first thing. So in that case, signal different path. Okay, so in this way we may send the signal, and there is a probability that signal will reach to the destination. Okay, and in this way we have a very good reliability will be not going to be broken. Is the time, okay, the different times these are the limited resources, you know, like frequency band is allotted by the government, and within that band you have to run your business, correct. The space, so these are the things, three things. Now apart from this, okay, because the subject started with the diversity thing, so the fourth is that we may introduce as the antenna diversity. Okay, this is antenna diversity. So here we may do the some innovation. Okay, so what kind of innovation? Innovation is like that: spatial diversity, and another is polarization diversity. Correct. So like we have already seen the number of system, like single input, multiple output, multiple input, single output, multiple input, and multiple output. So it provides the actually at the receiving and transmitting side. Fine. Another part is the polarization diversity. Let's say if we have a, just a minute. Polarization diversity. So like if we have one antenna operating in horizontal polarization, other is a vertical polarization. Okay. So we may expect actually less crosstalk in this way. Okay. Fine. So now this is a real example for you, correct? What is this? So a person actually some event, okay, with the camera. You can see this is camera actually, and here you can the camera. We have the okay, two wire antennas. Here you can see clearly two antenna, and this angle is, you know, can you guess? This is a 45 degree. Okay, so we are offering the polarization diversity here, correct? So in this way we may manage actually, and isolation part can handle. Okay. Now let us try to understand the MIMO multiple input and multiple output. So as we have seen that number of plus points MIMO, okay, because it offers the diversity, okay, we can improve the uh, link and system reliability, okay. So here you can see transmitter side and this is the receiver side. We have a number of antennas. Here 3 plus 3, okay, this is 3 antenna at transmitter side and 3 receiver side. Changes even if we change the antenna position amount. Okay, so this particular thing actually handled very well by this MIMO system. The second, it improves actually diversity performance. Now it comes with some disadvantages as well. One is the computational complexity. It's very high, and we are talking about the massive MIMO again. Okay, the picture is okay. Processing cost, fine. Now it comes with certain advantages as well, like it supports the very high data, correct? So I'll explain that how the high rate of data, high channel capacity, enhanced throughput, better reliability, and multi-path fading, reduced multi-path fading and bit error rate. Okay, bit error rate. Why? Because we are not modulation techniques. Because if you are increasing the modulation techniques, surely you will be having the high bit error rate. Okay, like if you are with the modulation technique, let's say 8 PSK, these things. Okay, so definitely it will be high the bit error rate. Okay, so by introducing the MIMO, we can handle this part of. Now let us try to understand how these things are working and how this diversity happening. The very first thing is like single input, single output. We already experienced this thing, and there is a high chance that we are getting lose the signal actually, because there are a lot of obstacles are available when we are talking about the critical scenario. Now let us take a very simple example, okay, of a single input and multiple output. Okay, so let's say we have an antenna here. Okay, you can see this is the antenna we have. This is the antenna we have, correct? And as multiple output, so at the receiving side we are placing antennas. You can see antenna number 1 and antenna number 2, correct? So for antenna 1 there will be a 2 path. One is that it will follow the black. Okay, it will go here, and this is, let's say this is the obstacle here, and it reflect back and getting at antenna number 1. The part will be this red line. Okay, so what is happening actually, we have a 2 antenna. Okay, but maybe due to some reasons, okay, the signal not reach at antenna number 2, and here we are enough lucky here that signal reaches particularly at antenna 1, okay, somehow these things. So now we are increase the probability of receiving the signal at the receiving. Say if we are so there is a high chance that we are having the have a signal, the connection will be lost finally, correct? But introducing one more antenna gives me chance actually to get, okay, chance actually, okay, this is a called probability. Fine. So the thing is, as I told you that uh, like if you are diversity scheme, so they are fading, these things fading in a different way, okay? So like here this antenna diversity you can see here, okay? So like if you if the antennas, so you are making your system too reliable, okay? These are the some of the definitions actually. Here you can see this is a single channel. Now here we have been introduced two channel paths, okay? So single input, multiple input, single output, like that. And here we multiple output, and considering the 2x2 system, so we have the definition of the channel capacity is like that, correct? So here actually provide me flexibility, so that I'm sure that I will be getting this, and in this way, correct, we are improving the system reliability. Now let us try to understand from these two. So this is come with actually the spatial diversity, and this is what actually is spatial multiplexing. So here there's a one data stream actually one. Okay, we are feeding and we are feeding each and every antenna. Correct, each and every antenna from all all the antenna we are sending the same signal. Okay, and let's say we are at the receiving end. From antenna number 1 and 2, the signal lost due to this multiple reflections or fading this thing. And let's say we are lucky actually that this antenna 3 signal reaches to the receiving side. So in this way, the spatial diversity concept came actually, that we can improve the ability of the system. Other than that, we can improve the data rate. How we can improve? Let's say we are providing 101, so we are feeding 1 to antenna number 2 and 2 antenna number 3. Correct. So happening actually like here, if I say this bit actually we are sending per 1 second. Okay. So it let's say 3 seconds. It takes the per bit 3 seconds taking transmitting the signal. Now here in a single shot, once is 3 bits. Okay, so in this way actually we can improve the rate. Okay, but here there is a problem now again, that we may have what we can do actually at the side, we may increase the number of elements, and in this way we may improve the probability of receiving the signal. Correct. So that is why this MIMO is very useful. Now let's say we have a data in this format, okay, and I'm using the QPSK modulation, correct? So this 01, 01, these symbols actually I have written, the 4 symbols I have, let's say, and let's say I have a window of 100 megahertz. So what I did actually, I divided in parts of 10 megahertz of each channel. Like you can see, 30, 40, 50 like that. Okay, so in this way, what is happening actually, when I'm introducing the modulation scheme, okay, I may improve the data rate. Correct. So it means that one symbol will be taking the 0.1 microsecond. Correct. So these things now introducing this QPSK modulation. Okay, so because we are combining the 2 bit in a single symbol actually, so it will be, we may expect that 20 bits per 0.1 microsecond. Correct. This is one way. By using the may improve the data rate. The second one is that if I introduce the 2x2 MIMO, correct, so what will happen? These 2 symbols, let's say symbol number 1 and 3, correct, we are sending by the 2 different antennas. So what will happen? At the same time, these 2 symbols are reaching at the transmitter side, so the bit rate, okay, or the data rate will be increased or maybe doubled actually. So we may expect here the 40 bits per 1 microsecond. Fine. So this is what that MIMO for 4G LTE communication. Correct. Some of the applications think about, like here you can see very well-known things. Okay, routers in our office or home. Correct. So all wireless products with 802.11n, okay, support MIMO. All these things. And defense, and we may deploy these things. We may also have the IoT nowadays. Okay, the cloud-based things. Actually, we may control things remotely. All our devices in our home. Correct. And vehicular communications and satellite communications too may be benefited with these MIMO applications. Okay, so let us take one. This is not very critical, but let us take, let's say, if we have no multipath and in channels, or only line of sight communication exists. Okay, let's say we are in some boundary condition where these things are not happening. So the purpose of MIMO will be lost. Correct, but this is just a imagination. It is not a critical thing. Correct. Now, because we are talking about the MIMO antenna, MIMO we have seen, and then we have seen the MIMO antenna. That how to validate the system, how to check the performance in a system. So for that, actually, we have parameters. Okay, parameters. Okay, by which we can say yes, this antenna system is working properly. Correct. So first thing is the isolation. Second thing is the isolation coefficient. Third is diversity. Fourth is total active reflection coefficient, and one is a channel loss. And finally, we have mean effective gain. So these are the 6 parameters, okay, by which we may actually check the performance of the antenna. Correct. So let us see one by one these things. Correct. Let us see one by. So first thing is the isolation between the ports. Basically, when elements more than the sense, let's say 2 or more. Okay, so we are finding S21, S31 like. So basically, in RF engineering, so you have to find it out S21, S31 like that. In this way, you can say what is the cross talking, or S23, S4 that. Okay, fine. And in literature, you will see that 15 dB ideal one. Okay, they consider this the ideal one, and this is particularly we supposed to. Now, this isolation is affecting very much to total efficiency. And here this is the relation. The radiation efficiency multiplied by 1 minus S11 square minus all the mutual couplings. Okay, here you can see. So if this is 0, so we may improve the total efficiency. Okay, theoretically, if I say this is 0, we may improve the efficiency. This is not process. We need to find the ways how to handle it. Okay, so like here, if you can see that example, if you take the mutual coupling between the antenna minus 10 dB and S11 is minus 10 dB. So for 2-port MIMO, the total efficiency will be 72%. Whereas if you're using the 4-port, this will be 54. So like if you improve number, okay, coupling between these two, you may improve this efficiency part. Correct. Now you can I believe we are getting this point, that why this isolation or is why this is dangerous for this communication part. Okay, so we are actually, you will see working how to reduce, how to improve these things. Okay, so basically I'm taking the isolation in a detailed way. Okay, because this is somewhat very important, And presently, if you do the literature survey, you will find the number of ways people are talking about this isolation. And like I divided in a parts. Okay, this isolation technique. Okay, I clubbed, and if I see the big picture, divided in 5 parts. First is the filter-based isolation technique. Second is that frequency, and this frequency selective survey maybe your metamaterials, okay, maybe your different kind of structures, maybe. Another thing is defective grounds. The very arbitrary things. Okay. Another thing is very mechanical thing, but people are using. Okay, is working very fine, but it consumes space. Antenna orientation. The last one is vector based or line. Some people are also saying lines also. Correct. So let me sorry. Just a minute. The slide came actually first. Before that, actually, I have to before I have to tell these things, all the definition first. Then we'll go. Okay, we'll go one by one all the. Okay, so as I told these things, as I told, sorry. The order I missed the order. Okay, so here there are 6 parameters are there. So this particular isolation I'll explain in detail. Okay, later on. Okay, and we'll mention these things are very important. So we'll cover then back to the isolation. Okay, okay. So this is the point, rearrangement problem. Okay. Is the correlation coefficient. It's very important, and it calculates the these things between the antenna elements. Okay, and let's say when your antenna is radiating, that how much these two are coupled in a far field region actually. So this is this things actually you can find in the envelope correlation coefficient. Fine, and the acceptable value is 0.5 here. Now this could be done with the far field and with the near fields, like S parameters or the far field. Okay, but the best part is try to find it from the far field, because it's the far field. Okay, this is not the near field, but this is a good estimation. Okay, this from the S parameter, this is a good estimation. You can check before going to measurement. You can check, and finally when you the measurement, you can cross verify that how much deviation and other thing. Okay. So like if you have the ortho of the antenna, okay, so you have the loop between the patterns. Are you getting this? Okay, let's say one antenna is radiating the horizontal side, other is vertical side. So you have a very less correlation. But both the antennas are radiating in the same, it will create a problem. To find the ways, these things. Second is the diversity gain. So diversity gain particularly is the increase signal to, okay, and due to the use of the MIMO system in place of CISO system or transmission, when MIMO system is reduced without the performance loss. So like this is actually ratio, you can say this thing. Okay, when we are system, and earlier we used the CISO system, so how it is efficient. Okay, how much actually having the less losses we are getting from diversity gain. Okay, and diversity gain is directly connected with the earlier definition, which is the ECC, is 1 minus ECC. Correct. So finally, we can also say this thing, diversity gain is defined as the SNR of the MIMO antenna system to SLR of the single port antenna system. Correct. So this is the simplest definition you can say. Correct. And nearly 10 dB this things is required for this number. If you see here that EC is 0, correlation is the maximum value is 10. Okay. ACC is 0.5, there will be some value. Correct. This is the things. Other is the total expansion. Okay. What is that? This is actually under root of all reflected power and incident one. This is same as S11, but here the number of elements are there actually. So we are estimating like this, and this number should be less than minus 10 dB. Okay. So TARC value, these things between, okay, this particular value is where all power are radiated, whereas it's all this incident power is reflected and nothing radiated. The same concept what we are experiencing the designing of antenna. Next one, and this could actually smartly with your S parameters. Here this is a definition. So channel loss is done minus log of pi r actually, and 511, 512, 2122 is defined as parameter. Okay, so the idea of maxi up to which the message can be transmitted continuously without losses. Correct, and the accepted value 0.5 bit per second per hour. Correct. And the last is the mean effective gain. Mean effective gain actually is the, you can say, the mean received power divided by the total mean incident. This is what we call the mean effective gain. Measure the effect antenna when effect of the environment is considered in a predefined wireless conditions. Okay, so this is actually the statistical measure of gain in a mobile environment. Okay, so we need to take care about this environment, like what we are saying, the channel actually. We need to take care about this thing. Okay, so like here you can see here, this is depends upon the G and P, where G actually the gain theta and gain phi, and this is the power actually here. So we may estimate, and finally we may also do with the S parameter as well. Correct. And like this is the definition. Like here, let us assume that you have two antennas, or you have 2x2 antenna system, MIMO system. You have to find it out MEZ1 and MEZ2. Like here, I MEZ less than 3 dB. Okay, this difference should be less than this. Okay, now coming over the type of the printed MIMO antenna. Basically, if you see, you will see number of things. Okay, doing with the MIMO antenna, but they are also side up. They are doing, they are use the based antenna and some other things also. Correct. Now here I focusing on the printed, because what we are correct. Other you may see these things like SIW and SI based MIMO, DR based people. First is the microstrip patch based. Okay, a different patch. Another important antenna. This is just nothing but you are repeating actually number of the element and keeping in mind that how to improve population as well. Other PFA antennas, so microstrip PFA, this thing, we can also make it MIMO distance. Correct. So these are basically three main sub things under which you will find a lot of papers on the MIMO antenna. Now, yes. So this is the technical level in literature. Correct. So as a, okay, in a previous slide, there actually I divided in 5. This is This is my personal this things view over these things. Okay, so I divided in five parts. Okay, this thing like filter based, FSS based, DGS based, orientation based, and reflector based. Okay, under that I'll put the examples here that how you can carry out the things. Okay, okay. So parasitic or neutralization lens. So like here you can see that you have, or this is the, if you manage, okay, if you manage the field direction in this way, so they will forming a odd mode here. They will forming a odd mode here, and in this way you can okay, you can manage your isolation, or the crosstalk will be less. Okay, so there will be less between these two elements. This is the foreign parasitic elements. Just a minute. Hello. अभी लेक्चर में हूँ, बस थोड़ी देर बाद बात करते हैं. And other thing is the metamaterial analysis base. Like here you can see the array of SRR. Now here, if I say physics about this thing, so here you have the current like this, and you have the magnetic field this. Okay, like if I'm considering this is XY plane, this is also the XY plane, and here if magnetic field will be the perpendicular of these things. Due to the property. Okay, this will be vertical. It's vertically coming outside, and it will be in YZ plane. So what is happening actually? There again is odd mode. We may reduce actually this isolation. Okay. Other parties are decoupling network based. Like here we like this is the paper I have taken, published in 2008, IEEE transactions. So this particular thing, like we have the decoupling network, we have an antenna, matching network, and all. Here you can see these things. Okay, we have two antennas here, and here we have a decoupling network. Correct. So this decoupling network acts as a stop. Okay, and we have a proper isolation. Other thing is that placement, and now here you can see this is one example actually I presented where I taken the inset feed of the patch antennas. Okay, you can see this is the antennas are there and orientation completely different. This is the orthogonal to each other. If you compare in these two, so you will find the 90-degree apart. Okay, so in this way, what is happening actually? There is a no cross talking as well as at the fall as well. Correct. So here this is the one paper actually published in 2016. So they actually put it like this. All elements are all okay. They put it, and if you really S21, so this is minus 25. So this is one of the easy way actually. I would say easy way to introduce the isolation enhancement. So we need to put the orthogonal first rule. Orthogonal to means orthogonality among the elements. Correct. We need to put it out. So in this way you can use the coupling effect. Okay, fine. Now this is DGS structure. Okay, so this defective structure particularly here you can see we're trying to make a LC tag. Okay, here this is a DGS. Okay, and this is isolator between the antenna elements. Okay, and particularly some points actually I have written here, like modification structure is use the mutual coupling as the current produced on the ground coupled to the adjacent and the high coupling between them. First part. So DGS, like I told you, this is particularly like you have to get the idea where the surface current is very high and this thing. So you may introduce this LC resonator there. Okay, so it may be going to stop by these things. Okay, and there will be less cross talking between the antenna elements. Okay, so here this is what some example. Actually there is a two monopole antennas here. Okay, and then this is actually the filter base. Okay, this is filter base. So we introduce a filter here, correct? You can see here filter, and we put it these two monopoles, and we have a very good isolation. Correct. This is one thing. Then we have this is actually reflector come DGS based, because here you can see there is a defected produce some defects actually the partial ground plane. In this way, and finally they put it. Okay, so some of the tangential electric fields are going to be zero. Okay, so in this way they improve the S21. Okay, improve the isolation. Okay, so one thing. So this is one paper actually they published 15. Okay, so they try to involve reflector and the DGS, both the things. Then finally we have the neutralization line. Okay, so why this neutralization? We have the two antenna elements, and we observing that there is a high current here. Okay, surface current. So what we are doing actually, we are trying a neutralization line. Okay, and we are arranging such a way that impedance is very low. So what is happening, that current will be short. We may introduce a very improved isolation between these two antenna elements. Okay, and there will be less crosstalk. Okay, so this is one thing. Another part is that electromagnetic band. So this is, we are making actually we are suppressing surface currents. Okay, like this is two stair antennas. Okay, this is the two stair kind of antennas here, and here this is a comb type filter, because the stop band kind of properties finally. Okay, so it will provide you the stop band property, so the surface will not reach to the antenna 1, 2, and this way we have a very good isolation. Correct, means all these things captured by this band gap structure. You may use band gap structure too. So the isolation, correct. And among these isolations technique, we used some of the techniques like filter based. We use the FSS based also. We use the neutralization as well. Now let me define here. Okay, it's very important actually, and we need to have the idea why two windows are there. Like one is a millimeter wave and sub 6 gigahertz, and which advantages for particular these things. Okay, so here, like when the technology actually we are talking about MIMO cognitive radio, when we are talking about sub 6 gigahertz, and when we are talking about the millimeter wave, so there is a two additional things are coming. One is the SIW, and is beam. So here, because we have required to handle the high frequency and power as well, and at very high frequency we may not expect actually omission pattern, because we require a very large. So what we are doing, we are making a phase array, so that we are communicating as required. Okay, all these things. So what are the advantages? That it travels a longer distance. Correct. It can connect also. Okay. Some of the cost of implementation is less, because already we have a structure and the number of less. But whereas if you're talking about the millimeter wave, we have the very good part here that we have very high data rates, and we have the low data as well. But the problem is that we have a very small size, and in that we have to incorporate the number of elements, because the frequency is very high. Correct. So both having the advantages and disadvantages. I'm not saying that this thing that millimeter this is bad or these things. Correct. Good actually, but when we are making when we are having not coverage on the data rate and other things. Okay, then this is no comparison with subsystem yards. Otherwise, when we are worrying well as so to use the subsystem, we don't have the alternatives for that. Okay. Now this is the design methodology. Okay, to decide actually as per the requirement what is needed and the antenna element bandwidth and other things. Okay, and finally you have to start with the single antenna. First you have to fix your single antenna. You have to the things that yes is working. Then you have to convert in MIMO. Okay, replicate it. Okay, maybe for 2x2 MIMO, it will consist of 4 antenna elements. Correct, and you have to make the isolation technique. So this is some of the routine work you need to perform. Now, actually, I would like to present here what we did at IIT Asim. So we started this thing in 2018. This MIMO, particularly printed MIMO. Okay, so this one of contribution is very good paper, and here the isolation we handle the two is the orientation, other is the decoupling network, and other best point is with the designer. This is a reconfigurable as well. Use the same antenna, okay, different frequencies. Okay, so this is the first kind of antenna you can say published in 2019, which having the capability of good isolation as well as reconfigurable system. Sorry. So here you can see. So this is an active antenna, and we use number of things. You can see the DC blocking capacitors are there. This is the biasing in this things. Okay, sorry, and this is the overall antenna design here. I'll explain these things. This is a pin here. I have to mention this is a pin diode actually for switching purpose. So this is actually the, so this is a single unit you can see, and here you can see the 90-degree apart. Okay, now here if you see, because I already told that if you are placing those antenna element 90, okay, having a good isolation, okay, improved isolation. But here you can see isolation is fine, but it is not very, you are not expecting the industry, because this is more than minus 10 dB. Okay, it's less than minus 5 or 6 dB, but this kind of number is useful. And why? What is the reason actually? The reason is that, okay, it's a very compact design. Okay, in the menu, you see here the kind of this thing structure which having a strong magnetic fields. Correct. Here, either introduce the high inductance. Introduce the high inductance actually. Correct. So this technique, orientation technique, is not at all here. So here if you see, like if I remove this Mender line inductor here, you will see here this is just a monopole. Still the isolation part is not good. Correct, and this could be very surface current. So what we introduce the decoupling network filter based this thing. So again we use the Mender line, and this is a virtual ground concept here, and this is a band stop kind of band stop filter. Correct. See these things. Okay. So when we have structure, okay, so this operates 2.5. You can see this thing. Whereas when we are removing certain part of this, it is working at 5.3 or 4 gigahertz. Correct. So one, if I and in between that, and I can manage the switching, so I can make some part of the structure is non-model. I put it this decoupling network between these two elements. You see here the 4 decoupling networks, and introducing, as soon as I introduce isolation less than -20 degrees, which is acceptable, correct? Similarly, when I remove the certain part of the structure, means a mental, so the same structure is working at 5.3 gigahertz with isolation as well. Okay, so it means that this decoupling is very fine here, and this could be done. This could be seen in from the like when we don't have this decoupling network, the crosstalk. But as soon as you use the decoupling network, reading from port number 1, you can see here there is a less influence of it. Similarly, other frequency too. Now that I try to find it out where I can put this pin diode, and it is making the off, make it non-model, so that we can switch actually between the two frequencies. Okay, so here you can see this is the pin diode we placed, correct, and here we have the DC blocking capacitor, and we have to bias it distance properly. So this is the circuit here, and these are the finally the S parameters. Okay, and we have seen the gain and S parameter, everything is fine. This is all 2 dB distance. Efficiency is around 75%. Active antenna numbers are not bad. Okay. The other part is that filter based isolation. Okay. So here particularly, this is the and okay, the monopole antenna you can see here. Okay, with a partial ground plane. When we introduce this filter band here, correct. So the isolation we improve more than 25 dB. Okay, and if you see the S parameters here, like this is T is for the when we have the okay. So here you can one is very high, very high. Okay, not at all we can say this is a MIMO antenna. But as soon as we introduce the filter, so we have S21 -25. Okay, so this could these things. This is the thing actually we developed first our bandpass filter. You can see this is the response of the bandpass filter connected over here. Now when you connect this, surely its capacitance and inductance will be changed. So what we did actually, we used the double stub matching here. So here we put it a double stub distance, you can see here, and we compensated the capacitance. As soon as we compensated, we have our big response. We published this paper in IT Electronics Letter 2017. Okay, so this is okay, the results are excellent and very well acceptable distance, and ECC and other values are very good. And this is one work actually we put it on unit cell and we try to make it as a circular unit as well. Okay, so this was one attempt. This is, I would say, actually like the structure actually somewhere. If you see, common is not a new structure. We just placed over this thing, and we found we found that it is working as a circularly polarized antenna. Okay. Now this is a recent one. In 2020 we published in IIT Microwave. Correct. One of MTech student and the PhD student, they performed this work. Okay. So like here, this is a slot. Okay. Slot based is the thing is like we have experienced that when we are using the slot antennas, we have very good far-field properties. Okay, so this is the one unit cell actually, bender line slot, and we couple from the back. Okay, okay, so it is resonating at the 3 different frequencies: 2.42, 3.56, and 5.46. Okay, so here you can see 3 bands are coming clearly, and particularly when we are changing a particular element, So a particular band is only going to influence. So in this way, we may manage, we may tune where we want other applications. Okay. Now after that, we use the element and we put it the two element MIMO antenna. So here you can we put okay like this, so that we can get actually some good isolation. Okay, mechanically. Okay, here you can see, and also things introduced on a DGS. Okay, this, and here you can see these are the three bands are there. Okay, and we have a very good amount of gain. Okay, this is first band is not good. Okay, but second band onwards we have a good amount of gain. Distance. You please check. Minus 1.1, 0.68 and 3.2. It's fine. But the thing is, this is not acceptable. This is not acceptable at all. We made attempt actually to have the multi-band antennas. Okay, but there are some limitations actually. Okay, and here the limitations are these parameters at all. Okay, and with this I cannot expect actually this work in a good journal. So we introduced this reflector. Okay, so we use this ring and small square inside things, and here you can see this is the experimeter of these things. Okay, so this is kind of stop band kind of things. This one, and the whole geometry we put it like this. We have a two element antenna and we have here the metasurface reflector. Okay, and we optimize certain parameters, and finally we have very here more than 4 always. Okay, and somewhat the bandwidth is also improved. Okay, with this AMC metasurface and PC reflector. So this is the overall result. Here you can see, yes. So these are the comparison. Yes, this is the width metasurface reflector numbers of the and metasurface reflector. This is easily include that these number. Okay, this antenna could be useful for many multi-band applications. Okay, and this is a radiation pattern here. Okay, this is a direction radiation pattern, very stable and frequent. We have checked. Finally, we also check diversity performance of the. We got very good numbers. 7.0 these things. Okay, and so these things you can see it's close to 10. Okay, which is a required number. We check TAR, CCL also, and here you can see this is a summary to overall. It's really very good actually. All the numbers are very good for all the, and finally we compare our work, very recent work, and we compare with the other triple band antenna. Okay, double band and triple band antennas, and what we found is really very good actually. All the parameters if you see it's very good. And here the main thing was that we introduced a suitable reflector which can compensate this for, and we got a very good numbers like gain and efficiency. Okay, so this is all about from my side. We developed number of antennas, correct? We developed a number of more antenna cognitive systems, antenna for system for cognitive design. Recently we claimed MIMO antenna which can handle your two different scheme. One is underlay and overlay. We mix actually. So all the things I cannot show these things, but surely, okay, some other stage I'll try to explain all the things in a detail. So this is all about from my side. Okay, and this is work actually we published in IEEE transaction Here the idea is almost same. I'm not going into detail. So this is particularly frequency surface, and we got the double one is the iso as well as the RC. Okay. So okay, so I'm not going into the things, Amit. Okay. So I would like to end the things, and thank you so much. And if you we would like to, I would like to interact with you. Okay. Thank you so much.
Thank you very much, sir, for giving so nice talk and giving insight about MIMO system. And also thank you very much, sir, for accepting our invitation in a